Okay, second semester, we're starting off with normal distributions revisited. It's revisited because honestly, almost all this lesson is review, which is good for a first lesson of second semester. So that's actually a good thing. Okay, so a continuous random variable takes on any value in between, some specified interval. And we're to use a density curve. Usually it's going to be a normal curve, but it could be something else, maybe uniform. Um, But what's always true about every density curve that we're trying to model the data with is that it always is above the horizontal axis. It's not like calculus. And it always has area of 1 or 100% underneath the curve. So that's the area of the curve is always 1. And so we're trying to find that probability that it hits between there. Let's start with the easy one. This is more of a uniform curve. She works at the Denver, this girl works at the Denver International Airport. She can either take the airport train or the walkway. She should walk just to get more exercise, but she wants to get there in 4 minutes. She wonders which way will be faster. So X is the journey time. That's our random variable we're measuring. Remember, random variables. We use a density curve to model this. So 4 minutes. So journey time is 4 minutes. So we want it to be there. That's the possibilities between. Let's see. This is journey time between 2 and 5 minutes is what we want here. Didn't really say that. So I thought the problem would say that, but this is what the density curve looks like for this problem, which is given to you. Now notice what should be the area of that rectangle there. In this case, it's rectangles. Usually it's a normal curve. Between 2 and 5 is 3. 3 times 1/3 is 1. So it's gotta multiply to make 1. Area of the base is 100. So the area is 3 times 1/3 or 100%. We want to calculate the chance that she gets there between 2 and 4 minutes. So that's the area we're shading there between 2 and 4. So now our length is just between 2 and 4, which is 2. So 2 times 1/3. The area under the curve of the interval we want is going to be 0.66 or 66.7%. So, and she'll get there, she'll get to work in less than 4 minutes, 66.7% of the time. A normal random variable, okay, we got that. Define the variable of interest. Fine to do that verbally. I mean, in this case, or write it down. Perform the calculation, show your work. I'll tell you what we need to show here. So one Brad baby tub has a dial on it to set the water temperature. It's pretty fancy. When the baby safe setting is selected and the tub is filled, the temperature X of the water, has a random variable, temperature X of the water, will be modeled by the normal probability distribution with a mean of 34 and a standard deviation of 2. The first step I want you to do, say, what work do I want you to show is, I mean, I guess you could write X as the random variable, the temperature there, but I would definitely draw the curve, right? So, and it said that the mean temperature was 34. I'm going to go 2 degrees to the right. I don't need a calculator to do this. I'm just going to do this by head. 36, 38. I'm going to go 3 standard deviations to the right and 3 standard deviations to the left. 32, 30, and 28. Okay, the question, doesn't say what the question is yet. Why is the temperature of the water in degrees for the randomly selected bath? Recall that, so why is the temperature in degrees Fahrenheit? And evidently they gave us Celsius. Oh man, we got to do some conversion here, right? So how would that affect, oh no. So let's just start over here. I didn't know there was going to be some conversion here. I didn't read the rest of the question. Definitely should have done that. Okay, so the mean, what's going to happen with the mean? So let's get our calculator out here. So the mean was 34. Let's see, does multiplying and adding, does that both affect the mean? I think it does. So 32 plus 9/5 times 34, I believe it was, is that. Which is 93.2 degrees. So that is our mean. What affects standard deviation of 2? So I don't think we have to do both. The only thing that's going to affect standard deviation is the multiplying. So 9/5 times 2. If I want a decimal, I'm just going to put decimal in there. I prefer the decimal here. 3.6. So I am going to need my calculator here, I think. So let's draw a normal curve now with the correct numbers. The mean is 93.2. Standard deviation is 3.6. So if you want to do that, you can, I like to type in the number 93.2, press enter, then hit plus whatever the standard deviation is, 3.6, press enter 3 times, and it does it 3 times. So that'd be 96.8, 100.4, and 104. And I'm going to type in 93.2, press enter, and then subtract the standard deviation, 3.6, press enter 3 times. Just a fast way to getting that, 89.6 to 886. Sorry, real sloppy here at 82.4. Okay, now let's see what the question is. We want to get the bathwater between 90 and 100 to be baby safe. Okay, so between 90, somewhere in here, and 100, somewhere in here. So we're shading in between there. So that's where we want. I'd like you to do the shading on your paper. This is the kind of work I want to see. It's beautiful work. It counts as showing your work here in some ways. You still want to use the calculator command. So you're going to use that norm CDF. I think it's lower. So lower is 900. Upper is 100. Sorry, 90. It is 900. No, it's 90. Sorry, it's 90. And then mean is 93.2. And standard deviation SD is 3.6, I believe. Sorry, I didn't fit that on the page too well, but that's the kind of work you need to show. You'll do that in your calculator. If you don't remember the syntax for that, it's menu 652. Lower bound is 90. I hit tab 100. Mean, it's definitely good practice to do this. Don't just watch me. And then 3.6. We should get the right answer. 78.35. 78.35. Oops. %. Okay, so let's see what they said. So what are the mean standard deviation? Remember about adding means, standard deviations. Adding doesn't affect standard deviation. So we want it to be baby safe, and that's going to happen 78.39% of the time. So we just went straight to the answer. We could have, just to remind you about what we could have done here. So I'm just going to mention this because you want to be able to do this. You don't have to do this every time, but if they ask about the z-score, you need to know z-score. Z-score is the value minus the mean, minus x bar, over the standard deviation. So like that first value is 90, right? So 90 minus the mean, which is 93.2 over the standard deviation of 3.6. That's z on the lower bound. And then z on the upper bound would be, I think it was 100 minus 93.2. If you do it that way and get the two z-scores, you could, like they did, use those in Norm CDF and then just put 0 and 1. It defaults 0 and 1, just take 0 and 1 for z-score and you get the same answer. It's only different because of the rounding, so it's actually totally the same. 78.35 there. Using table A, we won't use table A, by the way. Based on your answer to part B, should a parent feel comfortable using the babysitting setting? Well, be sure to answer the question. When using the baby safe setting, there's about a 78% chance the water temperature meets the recommendation for a randomly selected bath. It's not great. I mean, if you give 10 baths over 10 days, 2 of them won't be the right temperature. So they probably shouldn't be too comfortable with this, actually. So yeah, I'm with you. I think that's too. With babies, you just don't want to take that risk. If it's me, probably be okay. But babies, you want to be careful. Any sum or difference of independent normal random variables is also normally distributed. In fact, any linear combination of it will be normally distributed. Here's a reminder of how we calculate mean or standard deviation. This is just the formulas that you know that we used. This was like last chapter or two. It was pretty recent, so maybe you still remember those. Remember, even when you subtract, you add this, you change in the variances, add them, and take the square root to get the standard deviation of the difference. Okay. So the diameter C on the top of a randomly selected large drink cup at a fast food restaurant can be modeled by normal distribution with a mean of 3.96, standard deviation of 0.01. They're pretty accurate, right? They're all about the same size, but there's a slight difference there. So, I mean, it could be a little bit off, 0.01 for one standard deviation off. But L, the lid, has 3.98 with standard deviation of 0.02. So again, pretty accurate, but they don't fit sometimes. I don't know if you ever had, I've had that at Panera where the lid doesn't fit the cup. It just, you got to change lids or cups or something. You got to do something else. Assume they're both independent random variables. That's important for adding standard deviations, but not by more than 0.06. Okay, so let's find the mean and standard deviation of these guys, right? So let's see if we can do this one. So it says the mean of the first one was 3.96. The mean of the lid was 3.98. So let's see what we want to do. Do we want to find the sum or the difference here? I want to find out L has to be bigger, So why don't we do L minus C? So the lid is 3.98 minus that 3.96 is 0.02. That's the mean. Standard deviation, how do I do that? I'm going to take the square root of 0.02 squared plus I don't know if I did that in the right order, 0.01 squared, and that will be my standard deviation. So let's see if they do this for us. We are going to do L minus C. It makes sense, right? We're finding the difference. They're independent random variables. We're going to use our formulas, and we get those two values, right? So now we know we could actually draw this now, I believe. So we can draw a normal curve. So 0.02 is the mean. I'm going to, just a little bit hard to do these when the decimals are so big. So I'm just going to use my calculator here. Whoops. Sorry. So I'm going to do 0.02. Always type the first one in, press enter, and then hit plus 0.0224. So 0.0424, 0.0648, and 0.0872. Let's go the other direction, 0.02, press enter, minus 0.0224. So negative 0.0024, negative 0.0248, negative 0.0472. Okay. It needs to be bigger, but not more than 0.06. So let's look at where the shading should be on this one. So bigger means like zeros. It can't be smaller than zero, the difference. 0.06, somewhere in here is 0.06. So shading kind of all in here. There a lower bound and an upper bound there. And so you're just going to get your norm CDF for this guy. I'm not going to write it down this time, but you want to get credit. So you want to write this down. So menu 652, you write this down. It'd be 0, 0.06. Mean was 0.02, and standard deviation was 0.0224. Notice I didn't round a whole lot. Draw out 3 important characters there or something. Be fine. So that's 0.777 essentially. That'd be fine to round to that third digit. So 77.7% there of the time that's going to happen. What's the probability? Describe this in words. There's about a 77.7% chance that a randomly selected lid will fit on a randomly selected cup. Don't round it to 78. 77.7 would be fine, or 77.66 would be fine. Okay. I like both these practice problems. I think they're good. Again, I just want you to get in the habit. It's kind of like relearning something we just learned, put it all together. This needs to be like automatic. This lesson, you gotta just practice it again, do some homework, get in the swing of things and be like, I remember how to add standard deviations, means and stuff, and you can just do it. So like on this one, the airline must consider the total weight of all passengers, crew, baggage, and fuel when they plan how much fuel they need. That's actually true, I think. Recent study concluded the weight X of randomly selected passengers. So X is the weight, the random variable, the weight of a passenger, randomly selected. Can be modeled by a normal distribution with a mean of 75.6, standard deviation of 16.7. I'm not going to draw that yet because I want to read the whole question. Let Y be the weight of a randomly selected passenger in pounds. Okay, so X, the first one's in kilograms, the second one's in pounds. Okay, one flight, if the passenger weighs more than 250 pounds, we'll delay the flight. Okay, so might do some conversion here. So find the mean and standard deviation of Y. So we want it in kilograms, I believe. So, man, does it tell us? Do they expect us to know how to convert kilograms? Oh, 2.2 pounds per kilogram. Okay, so if you're converting this, we want to convert 250 pounds. That's LB for pounds. We want to convert that to kilograms. So I'm putting pounds down there, putting kilograms up top. So it says there are 2.2 pounds per 1 kilogram. So I'm going to divide, right, because that cancels out the units there, just like Dunlap's class. Okay, so we get 250 divided by 2.2. And so to convert, when we divide, would that affect standard deviation? I think it would, right? So 16.7 divided by 2.2. Let's see if we're right here. So mean is 166.32. Oh, I did the wrong thing. Yeah, the given was in kilogram was the mean was that. Oh, so I should have converted kilograms to pounds. I don't know why I took I took the max. The max could be is 250, and I pretended that was our mean there. So I did not do that right. So 2.2, so we would multiply by 2.2 going the other way. So we were converting backwards. We should have multiplied because we're going from kilograms to pounds. Okay, so I'm glad I checked that. Sorry about that. Just get back and swing of things myself, right? So evidently this is a pretty tough problem. Okay, so now we have our mean or standard deviation. So you would now just go ahead and get out your, just go ahead and draw it, right? So I want to draw a curve. Mean is 166.32. That's 32. Standard deviation 36.74. So 166.32. Press enter, plus 36.74 three times. So we get 203.06, 239.8, and 276.54. So I'm not going to do the left-hand side, but we could. But I know 250 is the number. Somewhere in there is 250. And we know we can't have more than 250 pounds here, right? So we're going to shade that way. We want it 250 pounds or less there. So, wow, that's going to be most of the time, right? So let's see what that is. So we're going to do norm CDFs. Let's see if they did it the same way, 250. Oh, we want to find out when it's greater. I'm just not on the ball here. I should read the question. If the passenger weighs more than 250 pounds, I was thinking we wanted the passenger to be less, so the weight doesn't cause a problem. So what's the chance of the passenger weighs more than 250 pounds? How often does that happen? Man, I don't know if you ever had this happen. You're sitting on a plane, there's an empty seat next to you, and then the biggest guy in the plane comes and sits next to you in that seat, and they're more than 250 pounds. I've had that happen numerous times. It's Murphy's Law. It's going to happen sometimes. Ooh, it's rough sometimes. One time there's a guy that works for the Grizzlies. I think he's like a maintenance guy anyway, but he was a big guy. He's probably 6'7", probably a former basketball player. But he was a big guy. He was definitely over 250 pounds. Okay, so we want to find out the greater than that. So we're going to use, so you're going to use norm CDF 250 to, I would just say, if they said 10,000, I would say infinity on your calculator. Mean is 166.32, standard deviation 36. So it's a 1.14% chance. So if you look at part C, it says, based on your answer to part B, remember 1.1%, should the airplane's pilot expect to need additional fuel? I mean, boy, that's a weird thing. So only 1% of what time you're going to need additional fuel. There's a small chance, because it's probably so small, the pilot should not expect to need additional fuel for the plane. I wonder if they actually weigh it, or they just put enough fuel so they're just past that. They don't have to worry about the 1% chance. I don't know. It's an interesting idea there. I wonder if they do weigh every bag, so they probably know how much the bags weigh. I don't know if they know how much the people weigh. I have a feeling they don't, but I could be wrong. maybe they have a way of weighing the whole plane there. But I think that the luggage, they actually, using technology, should know. So they could get a pretty good estimate with that. Anyway, I don't know, interesting question. This one, airlines must consider the total weight of all passengers, crew, baggage, and fuel when planning making fuel for a flight. Recent study concluded the weight of A, randomly selected airline passenger, can be modeled by a normal distribution. We already did this. The weight of the passenger C. So the weight of C of the passenger's carry-on bag can be modeled by a normal distribution with a mean of 7.6, standard deviation of 5. Assuming that A, B, and C are independent random variables, let T be A plus B plus C. So we're going to add up all three guys. So I'm just going to show you the answer here. We're going to add up all three of those in kilograms, right? So we get 99.1. And then add up the variances, so squaring each of the standard deviations, adding those up to get 18.31. Those are independent random variables, so we're allowed to convert into variances and add them. So if those are our mean and standard deviation, how much will it weigh less than 75 kilograms? So again, we're gonna, if I were you, I would graph this, right? So you get 99.1, you add 18.3, so 99.1 plus 18.3, 3 times. I don't really need to go that direction. I need to go the other direction. So minus 18.3, 3 times. So I'd get 80.8, 80.8, 62.5, and 44.2. And of course, I'm going to do that this direction too, but just for time here, man, this is a long one. So 75, what's the question ask? 75 kilograms or less, way less than that, right? So 75 is somewhere in here. So we're here, we're shading less than. So lower bound is negative infinity, norm CDF, upper bound is 75, putting the mean of 99.1, a standard deviation of, I believe it was 18.3, that's our one, 18.3. And then of course you're going to lower, upper, mean, standard deviation. You're going to label those and put it in to get your answer. And there you go. 0.0940, so 9.4% of the time. So maybe they do measure the carry-ons. I don't know. They don't actually know ever what my carry-on weight is. I don't think. I don't know. Okay, that's the lesson for today.